All right. Hi, everybody. Thank you so much for tuning into my talk. It's a pleasure to be here and a pleasure to share my work. So thank you very much to the organizers of this conference for this wonderful opportunity. My name is Kalina Nedkova. I'm a graduate student at Tufts University, and today I will be telling you about the size evolution of galaxy components, and specifically, I will tell you how galactic bulges have grown in size since a redshift of 2. So the work that I'll be presenting today is an extension of work that we published last year, which looked at the mass size relations of star forming and quiescent galaxies. And although these mass size relations have been extensively studied in the past, the piece that's new here is that we extended these relations to include lower stellar mass galaxies at redshifts of 0.2 to 2 than had been previously studied in past works. And so the main results of this study can be seen here in this figure, where you see the mass size plane in 4 different redshift bins, which are indicated here at the bottom. And so what we found was that for star-forming galaxies, for which the mass size relations are shown here in blue, well, these galaxies follow the same relation at the high mass end and the low mass end. And this is contrasted by quiescent galaxies, which you can see regardless of the redshift bin that you're looking at, they follow very steep relations at the high mass end and shallow relations at the low mass end. And so one way in which we can understand how these galaxies are evolving is by comparing these relations to lines of constant mass surface density, which are shown here in these figures as these diagonal gray lines. And so if the relation is steeper than these lines, then most of the mass in these galaxies is being assembled in the outskirts. Whereas if the relation is shallower, then most of the mass is being assembled within the inner 1 effective radius. And so just to indicate this on the slide here, if we look at the high mass quiescent galaxies, these are predominantly assembling their mass in their outskirts. And this is consistent with the idea that quenched galaxies are evolving as a result of repeated minor dry mergers, which are known to puff out a galaxy and significantly increase its size. And this is indeed very different from low mass galaxies, which are mostly assembling their mass in the inner regions. So now, if we want to play the same game for galactic bulges, then we would be able to say where galactic bulges are assembling their mass. And indeed, this is what we set out to do. And the first step is to decompose galaxies into their components, namely their bulge and disk. So to do these decompositions, we used the Megamorph tools, which consist of 2 codes, namely GalFit-M and Galapagos-2, which use information from multiple bands simultaneously and fit wavelength-dependent functions to the measured parameters. So this has several advantages. One is if you can imagine a case in which you have a particular band with a low signal-to-noise ratio, then the measured physical parameters in this band would be less reliable. However, in the multi-wavelength fitting case, the parameters are better constrained as a result of the other available bands. So effectively, using a multi-wavelength approach increases the signal to noise of your data, and this makes it a more reliable approach than, for example, single band fitting. All right, so in this figure here, I'm showing you the fitting results for one specific galaxy. And I'm not showing this because it's a particularly good fit, but I'm showing it because you can see the advantage of constraining the Sirsic index of the bulge. So for each galaxy, we have done 3 sets of models. We have a single profile model. We have a bulge that is fit with a free Sirsic index plus an exponential disk. And we have a classical Duval-Couleur bulge where the Sirsic index is fixed to 4, plus, again, an exponential disk. And so these 3 models are shown here. So here's the single profile model. You have the image, the model, and the residual. And then the next one, you have the bulge where the Sirsic index is fit as a free parameter. So again, you have the full model, the residual, and then the disk and bulge component independently. And then the same thing for the Duval-Couleur bulge. And so this object is chosen because we prefer the n equals 4 fit. And I'll tell you why. So if we look at the single profile model, you see that the Sirsic index is roughly equal to 1 in all bands. And so this indicates that this is likely a disk-like galaxy. Unfortunately, in the case where the Sirsic index of the bulge is a free parameter, the bulge is given a disk-like profile with a Sirsic index of 0.8, as you can see here, while the disk component is fit with this elongated profile because Galpha M is trying to minimize the residuals of this neighboring object, which you can kind of see on the edge of the image. All right, in the case where the bulge is fit with a classical Duval-Couleur profile, you can see that the disk model is quite reliable, and it is the bulge that is fit with an unrealistically large radius. And we prefer this set of models because both components are fit with the same degrees of freedom, and we are less likely to run into cases where the bulge is actually fitting a disk-like profile. All right, so now that we have the model, this one, we have to select a sample of bulges. And so the first step is to identify whether a given galaxy is better modeled as a 1-component object or a bulge plus disk system. So the natural metric that we might want to use is the chi-squared. Unfortunately, the bulge plus disk model will always have cleaner residuals because it has more degrees of freedom. And so instead, what we use is a decision tree, which is based on a number of parameters, including these down here. And it's rather involved, so I won't go through it. But basically, we use some combination of these parameters to decide whether a given object is better modeled as a 1-component or a 2-component system. And in the end, we have a bulge sample, which consists of both bulge components and spheroidal galaxies, which will become important a little later in this talk. All right, so the last piece of information that we need is the stellar masses of these galaxies so that we can derive the mass size relations. So one way to obtain stellar masses of the components is to use this relation between the mass to light ratio and color. And so what I'm showing you here on the left is this relation for the Hubble frontier fields, and again, this relation for galaxies from the Candles fields. And these relations are strongly dependent on the assumptions that are made when the stellar mass of the whole galaxy is obtained. So, for example, it depends on the initial mass function, the star formation history that is assumed, the dust law that is used, and so on. And so you can see that different people have obtained different mass to light color relations. And so because of this, we have decided to derive our own. And in fact, we find that the relations that we derive are quite consistent actually between the HFF and Candles. And so then the idea is that once you've done this for the whole galaxy, now you can take the color of the component and obtain its mass by using this relation. Okay, the other method for obtaining stellar masses that we've used is using the bulge to total ratio to determine the flux in the bulge and in the disk. So what we've done is we've taken the total flux and used the bulge to total ratio to find the bulge flux and the disk flux. And we fit these with a code called FAST. And you can see that for this example galaxy, we have several bands that we've used. And in black here is the whole galaxy from the 3D HST catalog. And then we have the bulge in red and the disk in blue. And the sum of these two components is shown here as a thin gray line, which you may be able to see. And in fact, we find excellent agreement between the sum of the components and the total galaxy that was fit from the photometric catalog. And so actually we find excellent agreement between this method of using the SED fitting from FAST and also from using the mass to light ratio. So we've compared both of the stellar masses where we obtain the stellar mass of the components. We've compared these to the stellar masses that are reported in Shipley et al. 2018, and these are both really consistent. So it doesn't really make much of a difference which one we choose, but in the mass size relations that I'll show you in a minute, we've chosen to use the mass to light ratio method. All right, so here is the bulge stellar mass size relation. So again, it's shown in the same 4 redshift bins that we looked at in the past. And this might look a little familiar because again, we're seeing some of the same features, namely at the high mass end, we see that the bulges are following these steep relations, whereas at the low mass end, the relations are quite shallow. And so just to remind you, this means that these high mass things are assembling mass in their outskirts and the low mass ones in their inner regions. And so just to highlight a few other things here, we don't find very many high redshift bulges, but this is mostly a result of our wavelength coverage in our fitting. And so this is something that we're actively working on now to obtain more high redshift bulges. And then the other piece is that it looks like these bulges are following a similar relation to the Van der Waal 2014 relation for quiescent galaxies. Okay, and so I just want to compare with some more recent work. In fact, this just came on the archive a few days ago. And so what they're showing you here is the size of the bulge versus mass, and the size of spheroidal galaxies versus their mass. And so what you can see here is that bulges really show no evolution in size with mass, whereas the spheroids sort of show this steeper relation here. And so at first glance, it might appear that our results are rather inconsistent, but as it turns out, these galaxies are predominantly these more massive spheroidal galaxies. Like I said, our bulge sample is comprised of both bulge components and spheroids. So the most massive ones are likely spheroidal galaxies. So these two are actually in full agreement. So what does this tell us about the evolution of galactic bulges? Well, first, we did not detect many bulges at high redshift, but again, this doesn't mean that there are no high redshift bulges. This is likely a result of our data And so we are actively working on increasing the sample size at these high redshifts. And the piece that I want to focus in on is that the high mass bulges, which are likely just spheroidal galaxies, are building up their mass in their outskirts, while the sizes of low mass bulges show no dependence on the stellar mass. So this has, I think, really important implications for the way that bulges can evolve. And so I will end it here, and thank you so much for listening.